Hello, Econometrics Appendix. This is a walkthrough from the first lecture of Appendix A, which is really the first day of class. And after getting through all the course, whatever administrative stuff, this is where we take off looking at the data section. And let's start off by talking about visualization. A picture is worth 1,000 words. And there are a lot of ways. Every data set has a story, and a visualization is a great way to extract the story or be able to interpret a story from a data set. I've got one right here, a bunch of numbers, and looking at these numbers, it's hard to tell what's going on. There's a lot of some tools we can use. A very handy tool is to turn this into a visualization graph. I'm going to throw this. I come up, click on insert. Let's make this a scatter plot. We can quickly see that this data set has a story. It's a smiley face. It's pretty simple, but I think here, what I wanted to just show with this is that having a graph or a visualization can go a long ways towards understanding what the data set is telling us. I made a data set using AI. I compiled it. The prompt I used was create a table with top 5 Filipino exports by year for 5 recent years, include quantity in dollars for each of the categories of the table. And I roughly had this table, and I played around with it just a little bit. And from that, I made these two tables right here. I'm gonna make some graphs out of this. The table looks nice, makes for a nice chart, but I think if we make a visualization, we can tell a story a little bit better. I'm gonna start off, go to insert. I'm gonna make a vertical bar chart, which is a pretty common chart. Let's label it. Vertical bar chart. And maybe if you want to, feel free to edit this. I'm going to do a couple of things on here. So let's give that a 20%, minimal overlap. It's going to just take a second, bear with me. There's a couple of things that I generally like. Let's change the font. 14. There we go. That looks a little bit better. I'm going to change, let's get rid of the decimal. And these are, if you give it a solid white line, it goes into a Word document with a white background, really easy to move around. I mean, you don't have to do this, but I'm going to add a couple of things. This is billions of dollars, just a little bit. Now I've got this nice vertical bar chart, and it makes it easy to compare in 2025 where the exports from the Philippines, what kind of things they produce. It looks like electronic products and really important. What if I want to make this a horizontal bar chart? I'm going to select this data, the Control C, and I need to get out of there. I'll paste it. I can recreate this chart using the methods that I just used with an alternate. I can grab this data right here, click insert, and then I can make my vertical bar chart. Another way is if I just copy this, I click on the data set, you notice I've got these little, these little blue circles around each of the squares. I'm going to change the series chart type to a horizontal bar chart. And that's nice. What if I want to make a pie chart? I've got the donut chart already here. I'm going to do the same thing. I'll just change it. It's a lot easier to tweak something rather than reinvent the wheel. I'm going to, let's make this pie. Choose chart type, and we'll make a pie. There's the pie chart, or if you want to make a donut, like the other one. And maybe I'm going to add some data labels. I'll format these data labels to show the category name instead of value. And then I can pull these out. And what you want to do is consider what your audience is. People who are analytical generally tend to prefer having the bar graphs. People who don't think of numbers as much might prefer pie charts. Think about your audience. So there's a couple of charts that we have. Let's make a bar graph, look at these categories, look at some longitudinal data. If we look at from each year, now this goes from 2025 to 2021. And so I'm going to sort this by year. There we go. And if I'm making this, what I'll probably want to do is just pick one of these. I'll pick the y-axis variable first. We'll do insert. Let's do a clustered column. That way we can have both electronics and machinery at the same time. And this it's not quite done, but it's selected. I've got a good start. Now that I have the Y in there, that's the billions of dollars. I'm going to click on this data. We'll do a couple of things. And I'm going to add the x-axis. If I come up here in the formula bar, the first one is the title. Then after that, there's a comma. The next input is the x. And the very last thing, I guess the third thing is the y values. I'm going to input the x values in here, which are, I can just pick the cells that have them. And then they show up down here. Now that I have the x values established, I can grab this other column, machinery, copy it. Control C is copy, Control V is paste. I select the table where I want it and I paste it. Voila. I've got it. And I think I want to add a legend below. Let me see what they are. And then maybe you can change, if you want to change the font, make it consistent with however your document has whatever tweaks. And for this one, I'm going to add a title, chart title. However, we call this Barber. But you'll want to use a title that's appropriate to whatever you're doing. So that's a bar graph. What if I want a line graph? I'm going to paste this over here. I'm going to change this. Oh, let's change this. So if I click on the data, if I right click, change series type, I can make them, well, let's do a scatter debug. I think I want to change scales. We have data from 2021, 2025, and that's it. And however you want to, but there's a few options, but this gives you a good idea of what the trends are. And with a bar graph it makes a lot more sense if you're looking at a continuous data set where one observation is related to this, if there's a sort of a sequence, the next observation actually looks to time. Time, you have 1 year to the next, and you look to see if it goes up or down, which is different from like these other bar charts that we had, where you're just looking at completely different categories that are unrelated to each other. So that makes sense to have a bar chart there. You can use the bar graph for year stuff, but probably having a line that shows a trend might make a little bit more sense. There's a couple of graphs. Let's look at frequency diagrams. This next one, I've got a table that, and here I've listed the source, but somebody interviewed a bunch of men and women and got their shoe size and their height. And based off of this, the formula that I used is unique and then sort. And I only had for all the women. I sorted it by ascending order. to show all the shoe sizes that were listed. Then I did a count if for everything, and I came up, and that can give us a frequency. Frequency that helps make a histogram. We have the frequency on here. It's basically just a bar chart. We'll label this histogram. Looks kind of ugly now, but we can fix that. How about Garamond? Garamond is a nice stately font. I'm going to get rid of all the spacings on here for a histogram. Now the shoe sizes aren't there, and so I'm going to add that in here, the x-axis. And sometimes Excel does a funny thing. I don't know what that means, F7 ampersand, and so I'm going to deliberately pick something wrong, and then I'll just adjust. So there's 19. I mean, now the shoe sizes are there. We've got this nice histogram. You'll notice with this table, I have looks like a fairly normal distribution. With this table, I did a cumulative frequency, and then I looked at the proportion of those. And what this will give us something called an OGIV, or it gives us the running total proportion. And so I'm going to, I'll just give. Let's make a OGIV chart. And I'm going to you can see the proportion as it goes through time. What if I want to make a combination histogram and OGIV chart? I'm going to copy this. Now that I have the histogram already here, what I can do is just copy the OGIV and drop it in here. But it tries to give it maybe not the format that I want. I'm going to click that, right click, change series chart type. And the OGIV, I want that to be a secondary access. But instead of question column, we'll make it a money. There we go. And then you can do whatever formatting you want. I'm going to make those. Now we have the combination of snippets. And if I don't want those decimals on there, I can either get rid of them here, or I can right click here and format them. We're looking at on the left axis, that's the count. Maybe you want to label these, I don't know. It might make more sense. So that's how you can make a combination histogram. Let's look at the scatter plot. This data set shows beet consumption for people from Malaysia, as well as the GDP per capita. A scatter plot, you can take two different variables and see how they're related to each other by creating a scatter plot, because it maps each corresponding value to each other. And this one, it looks nice, but we have the money on the y-axis and the meat on the x-axis. What this is saying, the way we generally would interpret this is how much money they make is depending on the meat that they consume. And I think, while we can find a really strong correlation between the two, that might be flipped. So I'm going to change X and the Y axis. And really all I do is I come up here. This is the X axis. I'm going to cut it, Control X. And then I'll paste it right over here. That way I'm swapping location of the X and the Y variables. Now we have the amount of money they make results in the amount of meat that Malaysians will consume. And this is pretty typical in most countries. Meat is a normal good, which means that when people make more money, they consume more. And we can see this with this data set. The higher the income, the higher the amount of meat supply. let's label this meat or supply consumption, whatever, per capita, wage, I think this goes to 2023. Yeah. Or however you want to do that. Here months and I font. Let's make it something that's interesting. And if Excel will do the fancy thing, it'll run a regression for you. If you click on the data, right click, just add a trend line, and that is a regression. I'm going to do display equation on the chart. So now we have the fancy equation. Later on in class, we'll learn how to derive that on our own using calculations. And generally, you won't do that. You let Excel run the regression for you, but you'll have this tools to be able to develop this on your own. And what this equation tells us is that if Malaysians didn't make any money at all, that X is the GDP per capita. If Malaysians made no money at all, they would consume 24 kilos of meat. And then they're going to, let's see, 0.0014. So for every dollar of GDP per capita increase, that's the amount of kilos. What happens if you, so for every $1,000 increase of GDP per capita, Malaysians will eat on average 1.4 additional kilos of meat. And that's what we get from this. Well, there's our scatter plot. It's pretty cool. What happens if you have a couple of functions? How do we graph them out? Y1 is 5 plus 0.5x. Y2 is 20 minus 2x. You just plug these in here. The first one is 5 plus 0.5 times x. This next one is 20 minus 2 times x. Then we can copy them all the way down. And then let's graph these. Let's see. I'm just going to pick one, insert. Let's make well, I usually like scatter plot, but then even if I make it into a line. So here's Y1. Oh, let me do this one. I'll do the other one first. Y2, insert. So we have the Y variables. What I'm going to do though, is I'm going to add the X variables in here. Here we go. Now that it's established, I could take the other one. I'm going to copy it, Control C, and I'll paste it, Control V. And we have the solution. We can take some time and do some algebraic manipulation, but this is pretty handy too. Except I'm going to make this easier to read. I'm going to update the axes. But so really quickly, by looking at this graph, we can see that the solution is x equals 6, y equals 8. Or we could take some time and go through the math and we can solve it algebraically. So there are so we're right there. Let's do a little bit of algebra review. If we have a couple of linear equations, there's multiple ways to solve this. A really common way is to use something called substitution. And with substitution, you solve for one variable. For example, let's use this one. This formula will be a little bit easier because we can solve for x. So that's a formula which we drop down here. I add y to both sides. You get x equals 1 plus y. And from there, you take this other equation that we have and plug in the x value, which is what we did right here. So x equals 1 plus y. So we have 3y plus y and 7. These two are going to sum to 4y. We're going to have y on one side. Let's take 3 away from both sides. Remember, when you do to one side and you do to the other. You're left with 4y equals 4. Divide both sides by 4, y equals 1. Once you have the y equals 1, pick any one of these formulas, whichever one you want. I'll just happen to pick the second one. Plug in your y, so x minus 1, which is y, is equal to 1. Add 1 to both sides, x equals 2. So we have our solution, x equals 2 and y equals 1. That's using the substitution method. The way I kind of prefer to do this, it's a little bit faster, is I like to add things together. And so what I'll do is I'll try to figure out how I need to multiply one of these, be able to add things and have the things go away. It's convenient that the x1s, we're looking at 1, y on both of these. And so they add together nicely. So if we add 3x plus x, we get 4x. Plus y minus y, you get 0y. 7 plus 1 is 8. So 4x equals 8. By both sides by 4. X equals 2. Then you see a little substitution. Plug that in, and you get the same solution. So that's a handy way to look at this. Is this solve? Here's a couple problems you can work out on your own. If you print off the handout from today's lecture, you'll have that. You work through those. The next slide shows these for these two equations. Or those two sets of problems. Let's look at the slope between 2 points. Slope is rise over run. So we have these 2 points over here. A is 4, 1, B is 2, 5. The formula is change of y divided by change of x. So make sure you're consistent with these. So you're looking at the y value, so y1 for A is 1 minus 5. And then for the denominator, we're looking at 4 minus 2. And that gives us, when we go through that, we get a solution of -2. Now, you can actually swap A and B, and you'll get the exact same answer. Make sure you're consistent, though, as in which one is 1, which one is 2, even if you're swapping them, and you'll end up with -2. If we take these same points right here and graph them, we'll get this, and we'll see that we go down. The rise over run is a slope, but we're going down by 2 over 1, and so that's -2, which is what we saw when we did these two calculations. For every 2 we go down, we go over 1. -2, we go +1, that has a slope of -2. Let's do a little bit of calculus. If you've never done calculus, that's okay. What really the portion of calculus can do all sorts of amazing things. What calculus is powerful, where it's really powerful is that you can look at rates of change. For example, when you're driving down the road, the speed you're going, the number of kilometers or miles per hour, that is the first derivative. That's the rate of change. And when you're navigating the hallways get pretty busy during class, you're very careful to not hit people. And so you observe the speed that people have. The second derivative is acceleration and deceleration. And those are things I think we at least intuitively do. Let's look at some numerical ways to do this. If you've never done a derivative before, there's a couple approaches. One is you turn it into the y equals mx plus b formula, and that can be pretty easy. So we have this formula 3x plus y equals 7. So we turn it into y equals mx plus b. Then you take your m value. You take the derivative of y with respect to x. This is -3, and you have the solution. If you want to do this mathematically, you take d over d of x times this. When you take the derivative of 3x, you'll take whatever the exponent is right here, and you multiply it by the number that's appended to the variable, and you'll get, and then you subtract 1 from this, so you end up with 3 of this, and then let's see. Oh, the derivative of x equals derivative of 7. That's going to be 0 because there's no x variable, so that basically goes away. So you end up with 3 minus d of y over d of x, so that's your unknown. which is equal to 0. You pull that on the other side, you get the same thing. And then there's another formula where you can solve the same, you can solve for that. And those are the equations we had from the previous example. If you have a more complicated, I forgot what it's called when it's up to the fourth power. I think if you just x squared, that's quadratic, and then I forgot the name of this type of a form. Oh, I guess it is a quadratic type of quadratic equation. So you take the derivative, take this number right here, you multiply it by that number. So that's what we have over here, 5 times 4. And you take this number and subtract 1. And that gives you this part of the derivative. And so you've got 20 times x cubed. Then where you have this cubed, that's going to be squared when you take the derivative. And so you take the 3 times 4, which is going to be 12, and then you subtract 1 from 3, which is going to be squared. So you've got negative 2x squared. When you have x squared, you basically pull 2 times 1, and you subtract 1. So it's going to be 2x. I guess we have here. That's a constant value that goes to 0. That's x times 0, and that's as far as you go. And this is how you calculate the derivative of something a little bit more complicated. There's some practice problems to work through. The next slide shows the solutions. Let's look at some exponents. These can look a little bit intimidating, but let's talk about each one of these. And I think you'll see that these are things you've done before, and they're actually quite easy. They're a lot easier than what these scary symbols look like. If the power or p is a positive integer, x times p is equal to, then we have this symbol, which means it's like summation, but you're multiplying for each of these. And so you take that x, this is the number of times you multiply it by itself. X times x times x all the way until you get p times. The example that I have, 2 raised to the 4th power. So it's 2 4 times. When you do that, 2 times 2 is 4, 4 times 2 is 8, 8 times 2 is 16, and that's the answer. That's all it is. The next rule we'll talk about is when you have an exponent, if the power is 0, the answer is going to be 1. All the math classes that I've taken when we talked about this, the textbooks or teachers really like to use infinite. I don't understand infinite very well. But for me, 5.6, let's see, $5.6 billion or billion, that's pretty much infinity to me. So I'll use that number. You take whatever number it is, raised to the power of 0, it's going to be. And this will be really powerful when we're doing some other calculations in the future. What happens if the power is negative? X raised to negative, all you do is you put it in the denominator. 1 divided by, and use a positive number. So 2 to the negative 3 really is 1 divided by 2 to the third, 2 cubed, or 1/8 or 0.125, however you want to express it. What happens when you multiply numbers that have different exponents? You can just add the exponents together. An example, if you have 2 to the 3rd power and 2 to the 2 cubed times 2 squared, really here's our 2 cubed portion, and our 2 squared. So if it's the same number right here, you can just add these two together, 2 to the 5th. So that's a little bit of a faster way, a little more efficient way to get to a solution. If you're dividing these, remember when we have the negative, clean this up just a little. When you're dividing these, you remember this rule right here. And so if you're adding, then when you're dividing here, you're subtracting. And I have an example, 2 raised to the 5th power divided by 2 raised to the 3rd power. Maybe all those years ago of when I studied computer science, I liked the number 2. But we were looking at 5 2's in the numerator, 3 2's in the denominator. These 3 2's cancel out those 3 2's, and you're left with 2 times 2, 2 squared, however you want to express it. Those are the first set of rules. Let's go over a couple of more. If you have x raised to 1 divided by the y power, that's this thing right here. So for example, 16 to the 1/2, that's the square root of 16, which is just going to be 4. If you had 16 to the cube root of 3 up here, then the value is going to be 2. Just 2 cubed is 6. And that's right. And whatever the number is, that's you put whatever number here that you have in the denominator of this. If you have x times p, if you have all this parenthetical statement raised to some power, this is where you multiply these two together. For example, 2 cubed squared, that's going to be, there's your 2 cubed, but it's squared, so you do it again. And so really that's 2 raised to the 6th power, or 64. When you're multiplying two numbers together, and the numbers are different, but the power is the same, you can multiply them together and then raise it up to the power. For example, 2 cubed times 3 cubed, that's 2 times 2 times 2 times 2 times 3. So really you can take that, multiply it, and then you multiply that by you take the product of that, multiply it by these two, take the product of that, multiply it by these two, and mix and match however you want to. Kind of the same thing. If you just do 2 times 3 raised to the same power. And so that's another exponential manipulation. The last one that we have is if you're adding a whole bunch of exponents together, really you can just, the number of times that you're multiplying the same thing is expressed by n times that. So you can treat that as a constant value and multiply it together by the number of times you have it. So 2 squared plus 2 squared plus 2 squared is equal to 4 plus 4 plus 4, which is 12, which is really 3 times, you're doing this 3 times, 3 times 2 squared, but 3 times 4 is 12. So those are a couple little manipulations you can use with exponents. There's some practice problems for you to work through. Next slide shows the solutions. Let's look at logs. Now, I left this in the generic form, although most of the time when we do calculation, we're using base 10. I think I have an example where I have something a little bit different. But, oh yeah, it's example right here. So if you're looking at a log base 4 of 16, if you had to take the log of something, and if it's a same number base as this raised to the power of something, then that's your solution. So a base 4 numeric system, taking the log of 16. Log 16 is really 4 squared. And so because these numbers match up, the solution is going to be 2. Okay, a textbook has different, I wanted to use something different from the textbook had, that's why I picked those random. If you're taking the log of some base number of x times raised to the z power, you can pull that z power out to the beginning. So z times the log of 4. For example, the log base 10 of 3 squared is the same thing as 2 times the log of 3. And here, I'll show you that in Excel. Stop drawing. Okay, let me clear this up. Okay, so I have so we're looking at this log formula, and the formula for log base 10 is log. And so we're looking at, let's see. Log of 9, which is 3 squared, is going to be 0.954, or 2 times the log of 3, if 3 squared is 9, you'll get the exact same thing. We can do the same thing if you're multiplying the log of a product of numbers. you can say the log of and add those two together. And where that's handy is if you have, for example, log of 3 plus the log of 2, really that's the same thing as the log of 6. And so let's see. Is log of 3 plus log of 2 or log of 6. Voila. You've got it's the same thing. Let's look at D. If you're adding those two together, it's the same thing as a product. If you're subtracting them, then you get the ratio. So it really is the same thing. The log base B of X is equal to the log B of, let's see, Y plus log Y of X. And the one thing I like to point out that is a common mistake, the log of X plus Y is not the same thing as the log of X plus the log of Y. In order to get to here, instead of adding, that needs to be multiplied. Okay, those are our logs. Let's take a look at the summation operator. And this looks really messy, but it's actually not. If we break it down, it'll make a lot more sense. The summation from I equals M up to N. And there you have some constant value. You can pull that constant value out here. So if you have, for example, 3 times 1 plus 3 times 2 plus 3 times 3, it's the same thing as saying it's 3 times the summation of 1 plus 2 plus 3. Where summation operators can be really useful is if you're adding lots and lots and lots of data together. It's important to think about terms in aggregate numbers, and that's what the power of the summation number does. If you're adding a bunch of constant numbers, the number of times you're adding them together, you can just say that number of times that constant, you get the same answer. If you're summing two numbers together and then adding the summation of those a whole bunch of times, you can just do the summation of one plus the summation of the other one. So if you have, for example, 1 plus 1 or 1 plus 2 plus 1 plus 2 plus 1, you do that 3 times. You can just do 1 plus 1 plus 1 and then sum that to 2 plus 2 plus 2. And that will give the exact same thing. Same thing with negative, but if you're subtracting, subtracting is really adding a negative. And so it's not that, so you can have, if you take the difference of those two and sum them all together, you can sum all of one and difference that with the sum of all together. It gets a little bit more complicated when you're multiplying things together. But here, let's take a look at how this works. X plus Y, then you square that, then you sum it over some number of iterations. Let's ignore this part for just a second. What happens if you take X plus Y and you square it? Then you get X times X, which is X squared plus XY plus XY plus Y squared. Really, you get this thing right. And this, so when you go from here to here, you're doing a little bit of multiplication, but it is a manifestation of what we saw in C, where you're just adding it together. And so, then also if you're going from here, you can parse it out into these individual summations and have the answer. The same thing when you're taking the difference between the two, you end up with X squared minus that plus that. And so naturally, if you're going from here, you should be able to go to here. The last one, we look at the summation operations. If see x1 minus x bar means the average or the expected value. If you take the average of the deviations and you take the difference between each value from the average of the deviations, you could end up with 0. You'll have all the pluses and minuses will compensate each other. Well, that's because you're taking the difference from the averages. So that's going to be physical. I've got an Excel thing to work through. We'll be set. Okay. And so, for example, there's a couple of formulas that have on your summation worksheet. One is sum product. if Juana wants to calculate her grade at the end of the semester, she has each of these categories have that type of a weight, either the score that she will earn or just earned or anticipates earning. To calculate her grade, you can multiply these. I just did a user input error. Multiply all these products together, and that will give you her grade. But what happens if you make a mistake, like I just did at the beginning? That was not intentional. It's easy to use your input error, but if you're only doing 5 of them, it's easy to figure it out. A more simple formula is sum product. It's color. If you look at 2 different arrays, it do the same thing like that other formula did, and you get the exact same result. Where something like sum product can be useful is if you are doing a sum product for dozens of records, it's easier to have some error when you're adding everything individually, so you can use the sum product, which should be the same thing. It's especially useful if you're doing 10,000 records, 10,000 rows. That's a lot of back and forth typing when you can simply just click sum product. There's a couple other formulas on the handout if it's useful for that. Let's look at the expected value, the very last part of this lecture. The expected value is just average X bar. So if the example that I have is my second son right now is in high school, which means he goes to early morning seminary. Pretty much every day he gets up somewhere between 5:15 and 5:30, and he gets himself ready and he gets some breakfast or whatever he does in the morning. Then he heads off to seminary, and he's there. It's constant. That's what he's done a whole bunch in the past. So I expect him that tomorrow morning he'll get up between 5:15, 5:30 and head out the door. That's what he's always done. And it's really the expected value. What happened in the past, we can anticipate will happen in the future. That's really the concept of it. There can be some variability in how things occur. If you're looking at trying to make a decision, understand the probability of success or failure can be dependent on how the response will vary. And so that's where variance is important. And you have, kind of a fun story. When I worked in fisheries, this guy called me up one day and he asked me to run some data for him. He told me, I want a letter certifying that my boat caught more fish than any other boat in this type of a fishery. And I thought, wow, that sounds, he's pretty confident of himself. And I looked through, and sure enough, that's where he was at. He told me a lot of really interesting things. But one of those is that when he was getting into fisheries, he called up my predecessor, the guy who had my position about 3 people before me, 3 decades earlier. And he asked him which one of these fisheries with this type of fishing gear and species has the highest amount of variability. And based off of that, and I think he recognized he had a skill set, and that's where he could have the most success, and that worked out for him. So understanding variance can be important. If you're trying to minimize risk, you want to minimize your variance. If you're not risk averse, if you're risk loving, then you want to have, like that one man who was a really good fisherman, then you want to look at where the variance is larger. To calculate the variance, remember the expected value is just the mean. You take the average of all of those variables and you take the difference from what occurred, and then you square that, and then you take the expected value of that. And the symbol we use is lowercase s squared x. The covariance is you're looking at the variance between 2 different variables. If it's positive, they're related. If it's negative, they're not related. A couple of rules. If you have a constant, you're going to end up with the same thing. Like my son, he's going to get up and go to seminary no matter what. There's no variability to that. You can just pull that out of the equation. If something lines up with your let's see, I'm looking at, you can pull out, let's see, A plus B times X, you're looking at expected value. B is going to affect X. And so that's the same thing as saying you can pull the constant out, but if the B is associated with the expected value, it's still going to affect that. And then you multiply it like that. And then the expected value, the variance of the sum of random variables, the variance of X plus Y is equal to the variance of X plus 2 times the covariance of XY plus the variance of Y. And if you want the derivation of that, you can go to the textbook. It's got a really good explanation. But I wanted to let's look at let's calculate some expected values. I have a data set of how long it took somebody to record a bunch of coconuts. The expected value, or the average time, I'm just going to type in the average formula. It's 3 minutes, 43 seconds. So if this data set represent what actually happened, we can pretty much expect that it'll be just under 4 minutes. Between 3.5 and 4 minutes is what will happen. How much does that vary? I wrote in some formulas in here. See, control tilde, that has the average, the expected value. I looked at the difference between that and the expected value, and I squared it. And to calculate the variance, you take the average of all of those together. Or you can use this formula called variance of a population, or VARP, and you'll get the same thing. So that's our first data set. The second data set, I don't know if it's a real data set or not. I found it on the internet, so it must be true. But it has 20 different students, the amount of time that they studied, the amount of time they spent on social media, and their test score. The expected value, how much did this class typically study? You take the average, the 13 hours. How much time do they spend on social media? Just over 8 hours. What is their average exam score? That is the average exam score is just under 80%. Now, if we have this data set where the variability is the variability is what informs us of how things happen. It's really important, which means that we can use covariance and come to some conclusions. Is study time related to getting a good test score? We're going to look at covariance of a population. Variance P. We're looking at study time, and we're looking at the test score. And according to the data set we have, yes, it's positive. And so there must be a positive relationship. You study more, you get a higher test score, according to this data set. Let's look at social media. Instead of studying, let's look at a substitute for time spent studying. Looking at social media, there's a negative relationship, which means you spend more time on social media, you get a lower test score. Now, this could very well be you spend more time on social media, that's a consequence of not studying as much. And that's probably what it is. Or you could go. Chapter 1, we're looking at covariance. I kind of prefer the correlation coefficient. And it's a unit-free measure of these two. And the numbers range from +1 to -1, -1 to positive. I just included that in there. We'll talk about this in chapter 1. Instead of I want J. And that gives us, that's a really strong correlation with close to 1. Anyways, I hope this format was useful for you. And great. Well, thank you very much for your attention.